A seemingly blank patch of sky hides one of space's greatest illusions. These are dark nebulae, colossal clouds of cosmic dust and gas so incredibly dense they blot out the light from every star behind them. By the end of this journey, you will know 25 of these enigmatic shadows that are actively challenging what astronomers think they know. We will explore why a perfectly dark sphere might be a star in waiting and what stops a massive cloud at our galaxy's heart from bursting into stellar life. What single cosmic mystery do you find most compelling? Hanging like a silhouette against the brilliant backdrop of the Milky Way, the Coalsack Nebula is a profound absence of light. For anyone in the southern hemisphere, it is a stark, dark patch right beside the Southern Cross, a void so pronounced you can see it without any telescope at all. This is not a hole in the universe, but a cosmic cloud, a vast and cold accumulation of dust and gas so thick it completely blocks the starlight from millions of stars behind it. Its apparent emptiness is a perfect illusion. Indigenous Australian cultures have recognized this shape for millennia, seeing not a void but a celestial emu, its head formed by the coalsack and its body stretching along the dark dust lanes of the Milky Way. This ancient interpretation speaks to its prominence in the human story of the night sky. Scientifically, its proximity at a mere 600 light-years away makes it a crucial laboratory. Astronomers study its dust grains to understand what these dark nebulae are truly made of and how their complex chemistry might be the very seeds for future solar systems. The coalsack raises a fundamental question. What exactly is the trigger that transforms such a quiet, dark reservoir of material into a blazing stellar nursery? It sits there, a cosmic cradle in waiting, holding secrets about the very beginning of star formation. While the coalsack presents a simple void, another dark nebula has been sculpted into one of the universe's most famous silhouettes. The Horsehead Nebula is an icon, a dark, brooding shape of dust that stands out against a faintly glowing pink background of hydrogen gas. Its recognizable profile is set within the immense Orion molecular cloud complex, a vast and turbulent stellar nursery located about 1,500 light-years away. This cosmic horse did not simply form by chance. It is a towering pillar, a dense knot within a much larger cloud, and it is currently under assault. Intense ultraviolet radiation from Sigma Orionis, a brilliant young star located nearby, bombards the nebula's surface. This radiation is slowly boiling away the lighter gases, a process astronomers call photodissociation, while the densest dust stubbornly resists, carving out that unmistakable equine shape. This creates a dynamic and violent boundary, a photodissociation region where the physics of destruction and persistence collide. Watching this process unfold in real time forces us to question the very lifespan of cosmic structures. We are witnessing the erosion of a masterpiece. The Horsehead Nebula is not permanent. In another 5 million years or so, that relentless stellar wind will have scoured it away completely, leaving no trace of the cosmic steed. Its temporary existence raises a profound point. How many other spectacular, short-lived formations have appeared and vanished across the cosmos without any witness? The universe is in constant flux, and these dark nebulae are fleeting characters on a grand galactic stage. Far from the violent erosion of the Horsehead, another dark nebula reveals a delicate and intricate beauty. Slithering through the star-rich fields of the constellation Ophiuchus, the Snake Nebula is a cosmic serpent woven from pure shadow. Its sinuous, filamentary body is not a solid object but a dense, cold thread of molecular gas and dust, so perfectly defined it looks as though it was drawn onto the sky. This incredible structure forces astronomers to ask what unseen forces can sculpt such a complex shape. The answer seems to lie in the invisible architecture of the cloud itself. Immense magnetic fields are thought to channel and constrain the turbulent motions within the cloud, guiding the material into these long, twisted filaments. It is a frozen snapshot of a dynamic battle where magnetic forces struggle against the chaotic pull of gravity. But the importance of the Snake Nebula goes far beyond its captivating appearance. By analyzing the specific properties of the dust grains within its dark coils, scientists can uncover the precise chemical conditions present there. This dust is the raw material for future planets, and its composition dictates what kinds of worlds can ultimately form. The nebula acts as a cosmic recipe book, its pages written in dust holding the secrets to what ingredients are available when a new solar system is born. What does the specific chemistry of this dark serpent tell us about our own origins and the potential for Earth-like planets elsewhere in the galaxy? Stretching across the star-dusted canvas of Ophiuchus, the Pipe Nebula presents a silhouette of startling clarity. This is not a single object, but a sprawling complex of dark clouds, with Barnard 59 forming the bowl and a long, stem-like trail of other Barnard objects completing its celestial form. It looks as though a giant has left its smoking pipe resting against the glow of the Milky Way. This entire structure is actually a part of the immense Ophiuchus dark cloud complex, one of the nearest major star-forming regions to our own solar system. Its sheer size and proximity, a mere 600 light-years away, make it a critical map for understanding the architecture of our galactic neighborhood. Gazing upon the pipe, astronomers are confronted with a fundamental question about the distribution of matter in space. How does such a colossal amount of interstellar material, enough to form thousands of stars, become organized into these vast, coherent structures? The Pipe Nebula acts as a nearby laboratory, its cold, quiet darkness representing the very earliest stages of star formation. Within its Inkai depths, gravity is only just beginning its work, slowly pulling together pockets of gas and dust that have not yet ignited into stars. By studying these pre-stellar cores, scientists can observe the exact conditions that must be met for a star to be born. It is a frozen moment in cosmic time, a pause before the storm of nuclear fusion begins. What subtle, invisible thresholds of density and temperature must be crossed to turn this silent reservoir of shadow into a brilliant, lasting light? Yet even these sprawling dark clouds can condense into something far more concentrated and stark. In the constellation Sagittarius, a tiny patch of absolute blackness sits like a hole punched through the fabric of the sky. This is the Ink Spot Nebula, known to astronomers as Barnard 86. Its profound darkness is made all the more dramatic by its surroundings, positioned directly beside the sparkling open star cluster NGC 6520. The contrast is breathtaking, a perfect jewel box of brilliant stars set right next to a pool of impenetrable shadow. This small nebula is not just a void, but a testament to the incredible density that interstellar dust can achieve. The dust grains within Barnard 86 are so thickly packed and efficient at absorbing light that they block out the light of every single star behind them, creating that perfect circular patch of black. This raises a crucial question about the nature of cosmic dust itself. Why is this particular cloud so much more effective at blotting out starlight than other, seemingly larger nebulae? The answer lies in the specific properties of the dust grains, their size, composition, and how they are packed together. But the ink spot's value goes beyond its striking appearance. Its location is a critical clue. It sits within a region teeming with stars and other nebulous objects, a zone that astronomers identify as the direction toward our galaxy's center. By pinpointing the precise distance to Barnard 86 and the star cluster next to it, scientists can use this dark patch as a landmark. It helps them trace the outline of one of the Milky Way's own spiral arms, mapping the grand architecture of our home galaxy. This tiny ink blot is a single data point in a cosmic cartography project, a small but vital piece of the puzzle in understanding the vast structure we are all a part of. But not all dark nebulae are content to remain as simple pools of shadow. Stretching across the southern constellation of Musca, the dark Doodad Nebula is a cosmic paradox. This long, slender filament of dust is so perfectly defined it looks like a scratch etched across the starry backdrop, a dark river flowing through the galaxy. Its whimsical name hints at its odd, almost artificial appearance, a celestial doodle that defies easy explanation. Its very existence presents astronomers with a pressing mystery. Given its immense length and the sheer amount of material it contains, the laws of physics suggest it should have collapsed under its own weight long ago. Gravity should have pulled this vast reservoir of gas and dust inward, fragmenting it into dense knots that would ignite into new stars. Yet the dark Doodad remains eerily quiet and dark, a sleeping giant that refuses to wake. This stillness forces a critical question. What invisible force is holding this structure together, actively fighting against the relentless pull of gravity? The leading theory points to powerful magnetic fields that run through the nebula's core like a cosmic skeleton. These fields could provide a form of internal support, creating pressure that resists gravitational collapse and maintains the nebula's slender, filamentary shape. The dark Doodad, therefore, is not just a shadow. It is a dynamic battlefield where magnetic and gravitational forces are locked in a silent, precarious standoff. By studying its stability, scientists are essentially probing the fundamental rules that govern whether a cloud lives a long, quiet life as a dark nebula or gives birth to a brilliant new stellar generation. What delicate balance must be maintained to keep a structure like this from tearing itself apart or igniting into a firestorm of stars? This apparent split in the Milky Way is one of the most dramatic features of the northern night sky. The Great Rift, or Cygnus Rift, is not a true emptiness but a colossal accumulation of dark nebulae, a series of overlapping dust clouds that stretch for thousands of light years along our line of sight. We are not looking at a gap between stars but through a dense cosmic forest. Each individual cloud in this complex is like a single tree, and when viewed from within the forest, they blend together into an unbroken wall of shadow that seems to divide our galaxy in two. This simple observation from our earthly vantage point forces a profound realization about the three-dimensional nature of the cosmos. Our view is not clear. It is filtered, obscured by a fog of interstellar dust that blocks the visible light from the countless stars lying beyond. This raises a critical and humbling question. How much of our own galaxy are we simply not seeing? The Cygnus Rift provides a direct answer. The sheer depth of this obscuration tells astronomers that there is a staggering amount of material between us and the galactic core. This dust fundamentally limits our view in visible light, hiding the true brilliance and structure of the Milky Way's heart. To peer into these hidden realms, we must rely on other forms of light, like infrared and radio waves, which can pierce the cosmic fog. The Great Rift is therefore more than a beautiful silhouette. It is a constant reminder of our limited perspective, a tangible measure of the veil that hangs before our eyes, challenging us to find new ways to see the universe. While the Great Rift is a sprawling complex of dust, one particular dark nebula stands out for its almost unnatural perfection. Barnard 68 is a near-perfect sphere of absolute blackness, a cosmic void so symmetrical it looks like a hole drilled into the universe. This object, known as a Bok globule, is a small, isolated cloud of cold molecular gas and dust. Its profound darkness is a direct result of its incredible density, with dust grains so thickly packed they absorb virtually all visible light from the stars behind it. This creates a perfect circle of nothingness, a stark ink blot against the starry background, but its true mystery lies in its symmetry and isolation. How does a cloud in the turbulent interstellar medium become so perfectly round and exist all on its own, far from the chaotic influence of other nebulae? The answer began to emerge when astronomers turned their infrared telescopes toward it. infrared light with its longer wavelengths can slip between the dust grains that block visible light. Peering inside, scientists discovered Barnard 68 is not a static object. It is a ticking clock, a cloud on the very verge of gravitational collapse. The entire globule is beginning to contract under its own weight, its core densifying toward the critical threshold needed to ignite nuclear fusion. This single, pristine sphere is a snapshot of a star system in its final moments of gestation. Its existence forces a critical re-evaluation of our models for star birth. If such a small, isolated cloud can spontaneously collapse into a star, it suggests that the initial conditions for stellar formation might be far more varied and subtle than we once believed. What does the impending transformation of this perfect dark sphere reveal about the quiet, solitary beginnings of most stars in our galaxy? The perfect symmetry of a lone Bok globule gives way to a far more dynamic and violent scene. In the constellation Monoceros, a monumental pillar of darkness rises from a sea of glowing gas, a structure so immense it could swallow entire solar systems. This is the Cone Nebula, a dark protrusion within the bright star-forming region known as NGC 2264. Its sharp, conical shape is not a random formation but the direct result of a ferocious cosmic wind. A cluster of brilliant, massive young stars located just off the top of the cone bombards the surrounding cloud with intense radiation and powerful stellar winds. This relentless outflow acts like a cosmic sandblaster, scouring away the lighter material and compressing the densest, most resilient dust into that iconic, pointed silhouette. The Cone Nebula is a living demonstration of stellar feedback, a process where newly born stars dramatically reshape their own nursery. This violent interaction forces astronomers to confront a deep and puzzling contradiction. The same radiation and winds that are actively destroying the nebula are also triggering new star birth within it. As the shockwave from the stellar bombardment slams into the dark cloud, it compresses the gas and dust inside to critical densities, creating the perfect conditions for new stars to ignite. The very force of destruction becomes the catalyst for creation. This delicate and chaotic balance is not yet fully understood. How can a process that tears a cloud apart also be responsible for building new stellar systems within its wreckage? The Cone Nebula stands as a monument to this paradox, a stark reminder that in the cosmic nurseries where stars are born, creation and destruction are two sides of the very same coin. The serene darkness of a cloud like Lupus III is profoundly deceptive. This sprawling dark nebula, a dense tapestry of dust in the constellation Scorpius, is not a quiet reservoir but a bustling maternity ward for stars. Within its opaque folds, dozens of infant suns, known as T Tauri stars, are flickering to life. These are stellar newborns, objects that have just begun to generate energy through gravitational collapse but have not yet ignited the stable nuclear fusion that defines a true star. Their presence creates a fascinating duality. On one hand, the thick dust of the nebula hides them from our view in visible light, just as it has for eons. On the other, that same dust is the very material from which these stars condensed. This active nursery forces a critical question. What was the specific trigger that upset the balance within Lupus III, causing so many different pockets of gas and dust to simultaneously collapse into stars? Did a shockwave from a distant supernova ripple through the cloud, compressing it? Or was it a more gradual, internal process where the cloud simply reached a tipping point of density? The evidence for this stellar baby boom is not just the stars themselves, but in the spectacular violence they unleash. Scattered throughout Lupus III are Herbig-Haro objects. These are not stars, but brilliant, narrow jets of superheated gas that scream away from the spinning protostars at speeds of hundreds of kilometers per second. When these supersonic jets slam into the slower-moving gas of the surrounding nebula, they glow with intense, turbulent light. Each jet is a direct, real-time look at the chaotic birth of a solar system, a sign of a baby star clearing away the leftover material from its formation. Watching these cosmic blowtorches at work makes the process tangible. It is a violent, messy affair, a far cry from the serene points of light we see in the night sky. Lupus 3 provides a complete picture from the quiet dark dust to the brilliant, explosive jets, showing us that the transition from shadow to light is one of the most dynamic and powerful events in the entire cosmos. While the chaotic nurseries of Lupus 3 blaze with stellar birth, a far quieter mystery unfolds in the constellation of Orion. LDN 1622 is a dark nebula so close to us, a mere 500 light-years away, that its silhouette appears immense against the sky. It is a ghostly presence, a veil of dust so dense it can be seen in both visible light and radio waves. This dual visibility offers astronomers a unique window into its secrets. Unlike the violent stellar feedback shaping the Cone Nebula, LDN 1622 is a place of profound quiet. It appears to be forming stars all on its own, in relative isolation, far from the intense radiation and powerful winds of massive stars. This serene activity challenges a fundamental assumption about how stars are born. For a long time, astronomers believed that most star formation was triggered by external forces, like the shock wave from a nearby supernova explosion or the pressure from a stellar wind slamming into a cloud. That external push was thought to be necessary to compress the gas and dust enough for gravity to take over. But LDN 1622 tells a different story. Here, low-mass stars are igniting in the deep silence, suggesting that some clouds can collapse under their own weight, reaching a critical density entirely through their own internal dynamics. This raises a pivotal question. Is this quiet, isolated star formation the rule, or is it the exception? How many other dark, unassuming clouds are secretly nurturing infant suns without any outside help? The existence of this nebula forces us to reconsider the true diversity of stellar nurseries, hinting that the universe may build its most common stars not in grand, explosive factories, but in the quiet, dark corners of the galaxy. But the quiet, internal collapse of a cloud like LDN 1622 is only one way a star can be born. Far away in the constellation Cepheus, a very different and far more violent process is sculpting a dark nebula into an unmistakable shape. The Elephant's Trunk Nebula is a sinuous column of cold gas and dust, a dark river winding its way through the glowing heart of the immense emission nebula IC 1396. This iconic structure, resembling a giant elephant's trunk reaching into cosmic waters, is not simply sitting there. It is under siege. At the center of the vast IC 1396 complex burns a brilliant, massive young star, pouring out intense ultraviolet radiation. This radiation acts like a cosmic blowtorch, heating the surrounding cloud and violently stripping away its outer layers of gas. The elephant's trunk is what remains, a dense, resilient knot of material that is being simultaneously eroded and compressed by this stellar fury. This violent process has a name: radiation-driven implosion. It is a paradox where external destruction triggers internal creation. The immense pressure from the radiation is crushing the trunk, squeezing the gas and dust within to incredible densities. And within that dark, compressed trunk, something remarkable is happening. Astronomers have identified small, teardrop-shaped knots of especially dense gas clinging to the tip of the structure. These are known as evaporating gaseous globules, or EGGS. The name is perfectly descriptive and perfectly grim. The same radiation that is compressing them is also boiling them away, slowly eroding them from the outside. It is a race against time. Can the material inside these EGGS collapse under gravity fast enough to form new stars before the external radiation completely destroys them? Each of these dark droplets is a potential stellar womb, a pocket of cosmic ingredients being forced together under extreme pressure. The Elephant's Trunk Nebula presents a stark question about the brutality of star formation. Is this how many stars, perhaps even our own Sun, came into being, forged in the violent crucible of a nearby giant's radiation? This nebula shows us that sometimes the universe creates new life not in quiet isolation, but by holding it in the fire. While some dark nebulae are cradles for new stars, others face immediate and violent destruction. In the heart of the running Chicken Nebula, a brilliant emission cloud in the constellation Centaurus, a flock of dark spheres is being systematically taken apart. These are Thackeray's globules, a group of Bok globules similar to Barnard 68, but their fate could not be more different. Instead of peacefully collapsing into stars, they are under a relentless assault. Just above them burns Lambda Centauri, a searingly hot, massive star that floods the region with deadly ultraviolet radiation. This intense energy is violently heating the surfaces of the dark globules, stripping their material away atom by atom in a process so turbulent it creates a visible halo of glowing gas around each dark core. The image is both beautiful and brutal, a cosmic demonstration of raw power. This scene forces a critical question about the fragility of star-forming material. Why are these particular clouds failing to collapse? The leading theory suggests their internal support is too strong. Perhaps powerful magnetic fields or even turbulent motions of gas within the globules are providing enough outward pressure to resist their own gravity. They are holding their shape, but at a terrible cost. The external radiation from the massive star is overwhelming that internal structure, boiling them away before gravity can ever win the battle to form a star. Thackeray's globules present a stark either-or scenario for cosmic clouds. They highlight the precarious balance between internal stability and external destruction. To successfully create a star, a cloud must collapse at just the right pace, in just the right environment. Too much internal support, and it remains a stable, dark globule. Too much external radiation, and it is erased from existence before it ever gets a chance to ignite. How many potential solar systems across the galaxy have been lost to the unforgiving light of a neighboring giant? This intricate cosmic tapestry reveals a far richer story than any single nebula could tell on its own. The Rho-Ophiuchi cloud complex is a sprawling, chaotic masterpiece of color and shadow, a region where dark dust lanes weave between glowing pink emission nebulae and ethereal blue reflection nebulae. It is a complete stellar ecosystem in a single, breathtaking frame. The dark nebulae here are not just passive voids, they are active, dynamic components, their dust serving as both a curtain and a crucial ingredient. This entire complex acts as a massive chemical factory. The thick molecular clouds are filled with complex organic molecules, the building blocks of life itself, forming on the frigid surfaces of dust grains. These simple chemical compounds are the precursors to amino acids and other vital substances. The presence of these molecules forces a profound question. How far does this cosmic chemistry progress before a star even ignites? Is the basic recipe for life written in these dark, cold clouds long before planets ever form? The complex provides a clear answer, showing that the path from inert dust to the potential for biology begins in the deepest, darkest recesses of space. The interconnected nature of this region raises an even larger point. Here, the formation of stars is not a single event but a spectrum. The same cloud can birth failed stars known as brown dwarfs, objects too small to sustain nuclear fusion, while also nurturing monstrous, short-lived giants that will one day explode as supernova. This coexistence is critical. The massive stars flood the surrounding dark clouds with energy, triggering further rounds of star formation, while the brown dwarfs represent the quiet, low-mass end of the stellar population. How does one vast reservoir of gas and dust manage to produce such a wildly diverse range of stellar objects simultaneously? The Rho-Ophiuchi complex suggests that the initial conditions within a cloud, the slight variations in density, temperature, and turbulence, create a cosmic lottery, determining whether a collapsing clump becomes a dim, smoldering ember or a brilliant, fleeting inferno. This single region encapsulates the entire life cycle of stars, from their chemical origins in the dark dust to their brilliant, interconnected lives, proving that creation in the cosmos is a deeply collaborative and chaotic affair. The delicate tendrils of LDN 1773 look like dark smoke frozen in mid-air. This intricate dark nebula is part of the much larger Ophiuchus cloud complex, a sprawling network of cosmic dust and gas. Its wispy, filamentary structure is far from random, a clear signature of immense forces at work. The nebula's complex morphology points directly to the role of interstellar turbulence, the chaotic supersonic motions that constantly stir the galaxy's raw material. But turbulence alone cannot explain such delicate, shredded forms. Astronomers suspect that another, more violent sculptor is at work here. Shock waves from ancient supernova remnants, expanding outward from stellar explosions that occurred millions of years ago, could have slammed into this cloud. These waves of energy would have compressed and ripped through the gas, carving the dark material into these ghostly, thread-like shapes. This raises a pivotal question about the very nature of star formation. Are the birthplaces of stars shaped by quiet, internal processes, or are they often forged in the violent aftermath of stellar death? LDN 1773 suggests that the final architecture of a stellar nursery, the specific layout of its dense cores, might be predetermined by these external cataclysms. The shock waves that sculpt the cloud also inject energy into it, influencing which pockets of gas will eventually collapse to form stars and which will be torn apart. This dark nebula is more than a shadow. It is a fossil record of past cosmic violence. Its intricate patterns a direct map of the forces that shaped it, forces that ultimately dictate where and when new suns will one day ignite. Rising like a monstrous fortress from a sea of stars, the dark tower in Scorpius is a spine-chilling silhouette. This colossal pillar of dust and gas stretches across 40 light-years of space, its spire pointing directly at a viciously brilliant group of massive stars known as NGC 6231. The entire scene is a dramatic tableau of cause and effect. The intense ultraviolet radiation and powerful stellar winds from these giant stars are relentlessly eroding the dark tower, blasting its surface and sculpting it into that iconic pointed shape. But this assault is not purely destructive. The immense pressure from this stellar bombardment is actually compressing the material at the edges of the dark nebula, squeezing the gas and dust to incredible densities. This process is known as positive feedback, a paradoxical phenomenon where the very forces that are tearing a cloud apart simultaneously trigger the birth of a new generation of stars within its ravaged borders. We are watching a cosmic chain reaction unfold. The death throes of one stellar neighborhood become the labor pains of another. The radiation from the existing stars is not just a destructive force, it is a sculptor and a midwife, pushing the dark cloud past a critical threshold and forcing it to create new suns. This raises a profound question about the interconnectedness of star formation. Is this how stellar birth often spreads through a galaxy like a wave, with each new generation of stars triggering the next in an expanding ripple of creation? The Dark Tower stands as a stark monument to this violent, self-perpetuating cycle, proving that in the cosmos, the end of one story is often the violent, brilliant beginning of the next. The brilliant glow of M78 often steals the show, a celestial beacon of reflected starlight in the constellation Orion. But the true mystery of this region is written in shadow. A complex web of dark nebulae threads through the bright gas, creating intricate, branching lanes of absolute blackness. These are not mere voids, but dense filaments of their own, a hidden architecture within the larger cloud. Their presence forces a profound question about the organization of matter in space. Is the interstellar medium structured like a fractal, where the same intricate patterns of filaments and knots repeat themselves at every scale, from a vast cloud complex down to the tiniest wisp of dust. M78's dark lanes suggest the answer is yes. This fractal nature means that star formation is not a single, monolithic event for an entire cloud. Instead, individual filaments and dense knots within the larger structure can reach their own critical density and collapse independently, like separate neighborhoods in a vast city, each deciding to build their own power plants. This explains the complex stellar populations we often find in these regions, with stars of vastly different ages and masses all existing side by side. They were not all born from the same single collapse, but from dozens of separate, small-scale collapses happening concurrently within the same grand cloud. The dark lanes of M78 are not just obscuring the view, they are active, dynamic sites of creation, proving that the path to a new star can begin on the smallest of cosmic scales. Barnard 343 drifts through a sea of hydrogen like a ghost ship, its dark silhouette only hinting at a deeper mystery. This nebula resides in a region glowing with the faint pink light of atomic hydrogen gas, a classic signature of the interstellar medium. Yet when astronomers pointed their radio telescopes toward it, searching for the telltale signature of carbon monoxide, or CO, a standard tracer for the dense molecular gas where stars are born, they found something unexpected. A profound silence. Barnard 343 appeared to be devoid of this crucial ingredient. This presented an immediate puzzle. How could a dense, dark cloud of dust exist without the molecular gas that should logically accompany it? The answer forced a fundamental revision of how we inventory the cosmos. Astronomers realized that our traditional method of using CO as a proxy for all molecular gas was deeply flawed. It turns out there are vast reservoirs of what is now called dark gas, molecular hydrogen that is not partnered with carbon monoxide and is therefore invisible to our most common observations. This dark gas is revealed only through more subtle techniques, like observing the faint glow of cosmic rays interacting with the hydrogen or using infrared telescopes to see the dust itself. The existence of this hidden component is staggering. It means our senses of the raw material for star formation, the very building blocks of solar systems, has been significantly underestimated. Barnard 343 is not an anomaly, it is a warning. How many other dark nebulae are secretly cloaking immense stores of this invisible fuel? And what does this missing matter mean for our models of how many stars our galaxy can truly create? This dark bay carved into the glowing coast of the North American Nebula is a cosmic landmark of profound scale. Known informally as the Gulf of Mexico, this vast indentation of shadow defines the southern border of the celestial continent, its inky blackness a stark contrast to the brilliant, ionized hydrogen gas that surrounds it. Its shoreline is not a fuzzy, indistinct boundary but a remarkably crisp and defined edge, as if drawn with a ruler. This sharp delineation is the key to its mystery. It forces astronomers to ask what physical processes can create such a clean separation between light and shadow in the chaotic interstellar medium. The answer lies in the violent interaction at the nebula's edge. The same massive, hot stars that cause the entire North American Nebula to glow are also bombarding the dark cloud with intense ultraviolet radiation. This radiation creates a shock front, a precise boundary known as an ionization front, where the energetic photons strip electrons from the atoms in the gas. At this front, the bright, ionized gas meets the cold, neutral atoms of the dark nebula. The sharpness of the Gulf's coastline tells us that the density of the dark cloud must drop off extremely rapidly at its border. It is not a gentle slope from dense cloud to thin space, but a sheer cliff face of gas and dust. By meticulously mapping this shoreline, scientists can measure the pressure balance between the two regions. They are essentially reading the history of an ongoing battle, watching as the light from newborn stars systematically erodes the dark, primordial cloud from which they themselves were born. How long can this dark gulf hold its shape against the relentless stellar onslaught, and what will be left behind when the light finally wins? Deep within the murky currents of another dark cloud, a tiny, dense knot known as CB133 presents a different kind of mystery. This is not a grand, sculpted pillar or a sprawling filament, but a small, isolated core of incredible density and cold. Its temperature hovers just a few degrees above absolute zero, a state of profound frigidity where molecular motion nearly ceases. This object is a textbook example of what astronomers call a pre-stellar core. It is a star in its absolute final stages of waiting, a pocket of gas and dust that has condensed to the very brink of gravitational collapse. All the ingredients are assembled, the density is climbing, and gravity is poised to take complete control. Yet the core remains in this precarious state of suspension, a cosmic pause button held down by forces we are only beginning to understand. The existence of CB133 forces a question of exquisite precision. What is the final, invisible trigger that pushes a core like this over the edge? Is it a subtle, internal shift where the outward pressure from microscopic gas motions can no longer support the weight of the cloud? Or does it require an external nudge, a gentle shockwave from a passing spiral arm or a distant supernova, to provide that last bit of compression needed to ignite the furnace? Studying this specific core is like watching a single raindrop clinging to a leaf moments before it falls. We can measure its mass, its temperature, its chemical makeup, yet we still cannot predict the exact moment it will surrender to gravity and begin to shine. This tiny, dark speck holds the secret to the very first heartbeat of a star, the definitive transition from a quiet cloud of dust to a brilliant, lasting light. How many of these silent, waiting cores are scattered throughout our galaxy, each one a potential sun, suspended in that final, breathless moment before creation begins? Lurking in the chaotic heart of our galaxy, a dark behemoth defies all expectations. Known to astronomers as the Brick, this dark nebula is a monstrous cloud of gas and dust containing over 100,000 times the mass of our own Sun. It is one of the most massive and dense clouds ever discovered in the entire Milky Way. Given its incredible mass and its location deep within the galactic center, a region of immense gravitational forces and extreme pressure, logic dictates that the Brick should be a frenzied stellar factory, blazing with the light of countless newborn stars. Yet when astronomers point their telescopes toward it, they find a profound and puzzling silence. This colossal reservoir of raw star-making material is eerily quiet, showing almost no signs of the vigorous star formation that should be tearing it apart. This contradiction lies at the very heart of the star formation mystery at the galactic center. Why is this cloud under such immense pressure not forming stars prolifically? What invisible cage is holding back the force of gravity? The leading theories point to powerful internal forces fighting a silent war against collapse. Intense magnetic fields may be woven through the cloud like a cosmic web, providing a form of structural support that prevents the gas from fragmenting and condensing into stars. Alternatively, the cloud might be filled with supersonic turbulent motions, a chaotic churning of gas that creates enough internal pressure to resist its own weight. The Brick is not a failed nursery, but a paused one, a ticking clock held in stasis by physics we are only beginning to comprehend. Its existence forces a fundamental question about the diversity of cosmic environments. Does the recipe for star formation change in different parts of a galaxy? It appears that in the violent, high-pressure core of the Milky Way, the rules of creation might be written differently, and this dark, silent giant is the key to deciphering them. This dark nebula hides a brutal secret. G3 50.1-0.3 appears as a simple smudge of cosmic dust, but it is actually the ghost of a cataclysm. This is a supernova remnant, the expanding shell of debris from a star that died in a titanic explosion, now cloaked in a shroud of its own creation. When that massive star reached the end of its life and detonated, it did more than just tear itself apart. In the unimaginable heat and pressure of the blast, it forged a rich dust of heavy elements, atoms like iron, silicon, and carbon that were synthesized in its final moments. This newly formed dust was then ejected outward, expanding into space along with the remnant's gaseous shell. Over time, that ejected material cooled and condensed, creating a thick, dark veil that now hangs in front of the expanding shockwave, obscuring our view of the violence within. This presents a fascinating cosmic irony. The remnant is being hidden by the very elements it created in its own death. This unique object forces a fundamental question about the grand cycle of galactic material. How does the death of one star directly contribute to the birth of another? G3 50.1-0.3 provides a direct answer. The heavy elements now locked within its dark dust are the essential seeds for planet formation. The iron that will one day form a planet's core, the silicon for its rocky crust, and the carbon that is the basis for life, all were born in that stellar explosion. This dark nebula is not merely a relic of destruction. It is a cosmic delivery truck transporting enriched material across the galaxy. When this dust eventually mixes with a pristine molecular cloud, it will provide the heavy elements necessary to form terrestrial planets and perhaps even living organisms. The end of one star's story literally becomes the raw material for the next generation of solar systems, raising a profound point about our own origins. Every atom of heavy element on Earth and within our own bodies was once forged in the heart of a long-dead star and scattered by an explosion just like this one. How many of these dark, self-obscured remnants are drifting through the galaxy, silently seeding the void with the very ingredients for worlds like our own? The violence of a stellar nursery carves cosmic sculptures with terrifying precision. The Tadpole Nebula, officially known as IC410, is a brilliant cauldron of glowing gas, but its real story is told by the dark shapes swimming within it. Two long, tadpole-shaped globules of cold dust and gas drift through the searing heart of the nebula, their dark heads and streaming tails a stark contrast to the surrounding inferno. These are not mere shadows, but dense, resilient cocoons. They are being shaped and eroded by the very same force that might be creating new solar systems inside them. A cluster of massive, scorching young stars at the nebula's center bombards the entire region with intense radiation and powerful stellar winds. This relentless outflow is boiling away the less dense material around the tadpoles, sculpting their long, flowing tails and compressing their dark heads to incredible densities. This is a race against time on a cosmic scale. Inside each tadpole's head, the crushing external pressure may be triggering the collapse of gas and dust to form new stars. Yet, this same environment is brutally hostile to the delicate process of planet formation. This paradox raises a critical question. Can the protoplanetary disks of gas and dust that naturally form around infant stars survive in such a violent neighborhood? The radiation and winds from the massive stars threaten to strip away these nascent disks before planets can even begin to coalesce. The tadpoles of IC410 are therefore a dramatic experiment in progress. They challenge our understanding of where planetary systems can take root. If planets can form and persist within these beleaguered globules, it vastly expands the potential habitats for solar systems across the galaxy, proving that even in the most hostile of cosmic environments, the stubborn ingredients for new worlds can cling to existence. Yet even this violent, radiant chaos can be born from a place of profound darkness. LDN 1157 appears to be just another quiet, dark nebula, a simple smudge of cosmic dust in the constellation Cepheus. But within its cold, opaque heart, a furious drama is unfolding, one we can only witness by listening to the whispers of molecules. Deep inside this dark envelope lies an extremely young protostar, an object so newborn it has not yet even begun to properly shine with thermal light. It is a stellar embryo still swaddled in its thick, dusty cocoon, yet this hidden infant is already unleashing a terrifying power. From its poles, it is firing out colossal jets of gas moving at hundreds of kilometers per second. These are not the gentle outflows of a mature star, but the violent, focused eruptions of a system fighting to be born. We cannot see the protostar itself, but we can see the devastating impact of these jets as they slam into the surrounding cloud, creating brilliant, shock-heated knots known as Herbig-Haro objects. This incredible activity raises a fundamental question about the very first moments of a star's life. How can an object this young, still actively gathering mass from its surrounding envelope, simultaneously eject so much material back out into space with such ferocious force? This is the central mystery of the accretion-ejection connection. It appears that as gas and dust spiral inward onto the growing protostar, an enormous amount of energy is released. Some of this energy is channeled and focused by the protostar's nascent magnetic field, launching a fraction of the incoming material back out into the cosmos in these spectacular, opposing jets. These outflows are not just a byproduct, they are a crucial part of the engine. By carrying away excess energy and angular momentum, they actually allow the rest of the material to continue falling onto the star. Without this violent release valve, the protostar might not be able to gather mass effectively at all. LDN 1157 gives us a rare and direct look at this feedback loop in its most extreme form. It forces us to wonder if this violent, self-regulating birth cry is a universal phase for all stars, a necessary tantrum that every sun must throw in order to finally settle into a stable, shining life. The final dark nebula on our list is one we cannot see with our own eyes, a ghost written in the language of cold. G11.11-0.12, known informally as the Snake infrared dark cloud, is a colossal filament of dust and gas so profoundly cold and dense that it is utterly black even to most telescopes. It reveals itself only in the longest wavelengths of light, in the faint whispers of the far infrared and radio spectrum. This is not a simple shadow against the stars, but a shadow against the very warmth of the universe, a river of absolute cold flowing through the galaxy. Its existence forces a monumental question. How does the chaotic interstellar medium organize itself into such an immense, coherent, and thread-like structure, stretching for dozens of light years? The Snake is more than just a cloud. It is a cosmic blueprint, a direct glimpse at the cold, dense precursors to the most spectacular stellar factories in the universe, the massive star clusters. Within its dark coils, the potential exists not for a single sun, but for an entire metropolis of stars, all born from the same colossal reservoir. This raises the ultimate question about stellar destiny. What subtle difference in the initial conditions of a cloud like this determines its final outcome? Why does one dark nebula quietly form a handful of average stars, while another, like the Snake, is destined to ignite into a blazing cluster containing thousands? The answer may lie in the intricate balance of forces within the filament itself, the specific strength of its internal turbulence, the precise configuration of its magnetic fields, and the exact distribution of its dense cores could be the deciding factors. The Snake is a frozen moment, a cosmic crossroads where the future of an entire stellar population hangs in the balance, challenging us to predict whether this particular thread of darkness will remain a quiet river or erupt into a firestorm of stellar light. These 25 dark nebulae have taken us on a journey from our own galactic backyard to the violent heart of the Milky Way. Each one, a silhouette against the light, has proven to be so much more than an empty void. They are cosmic cradles where stars are born in silence or forged in fire, chemical laboratories brewing the ingredients for future worlds, and dynamic battlefields where gravity, magnetism, and radiation wage a constant, invisible war. Their apparent darkness hides the deepest secrets of our universe, raising fundamental questions about how a cloud of dust becomes a star, how our galaxy structures itself, and how the death of one star seeds the birth of the next. The next time you find yourself under a clear, dark sky, look up at the shimmering band of the Milky Way. Pay close attention to the dark spaces, the rivers of shadow winding through the starlight. Remember that you are not looking at emptiness, but at a universe of potential, a canvas of creation waiting in the dark. We would love to hear which of these enigmatic shadows captured your imagination the most. Was it the perfect sphere of Barnard 68, the violent erosion of the Horsehead, or the silent, puzzling mass of the brick? Let us know in the comments below. And if you enjoyed this deep dive into the cosmos, be sure to subscribe for more journeys to the mysteries of our universe.